Yes, we can start. Right. It's my pleasure to introduce Jim from our studio. And he's been working on a number of things, but today he'll talk about extending the syntax of R without changing the language itself.
That's right. Thank you. Like Jan said, my name is Jim Hester, and I'm a software engineer at our studio. My primary responsibilities are working on the tidyverse set of packages and other infrastructure packages. Oh, and there's not that many of us, so you should probably be able to see okay, but if not, the slides and all the demos are available at this link, and they're just on my GitHub, so go there if you need it. So what does the typical R user look like? So R, this plot is showing the from the Stack Overflow survey from 2017, and on the x-axis is showing the average percentage of visitors across all Stack Overflow on a log scale, and then the y-axis is showing the year-over-year growth of each of the programming languages, and each point is a programming language. So R is up here. So of the languages that are fairly large, it's growing quite rapidly. This is a different plot showing similar data. R in this case is the blue line. You can see in the last like five years or so, it's had pretty rapid year-over-year growth on the Stack Overflow. So it's clearly a language that has a growing ecosystem. So what fields are users coming from? The top two fields here are academia and healthcare, but there's also a wide variety. And so that's like the vast majority of our users, or at least the majority of our users are coming from those fields. But also there's a long tail of variety of other places, even finance and insurance, government jobs. And there's some tech usage, but it's fairly low. So where did R as a language come from? Most of this growth has been in the last few years, but R as a language has actually a long history. So R is an implementation of the S language. S was first introduced in 1976 back in Bell Labs. And at that time, it was really a wrapper around Fortran modules, and also had like a M4 macro interface as well. And some contemporary languages with S in that time were APL, SPSS, another statistical package, at SAS, and C was also at Bell Labs as well. So that first, the next major implementation of S was new S in 1988, and that really introduced first-class functions. This is much closer to R and S that we know today. That introduced first-class functions and was implemented in C. In 1993, Modern S was released. That's my title. It's not necessarily the official title, but that is really very similar to what we have today in R. That gave us S3 classes, the formula interface, and data frames, which is some of the most important things today. So R was really an implementation of that version of S, that version in 1993. And originally, so the main differences of R versus S, R was really meant to be backwards compatible with S. The interface is almost identical to S. The main differences are in R, it used lexical scope, and also used, rather than having data on disk and reading all the data sets from disk, all of the data in R is in memory. The other next major advance was in 1997, R was open sourced and added to the GNU project. And I think this is one of the main drivers of its adoption in the coming years, was that it was both open source and also free to use, compared to some other alternatives of statistical software like SAS and SPSS and S+, which you had to pay for a license. Having R be free for students and others to use was a really big driver of its popularity. And since that time, R has gone through a number of additional revisions. R 1.0 was released in 2000, and that's really when it started having sort of exponential growth, which has brought us to where we are today with R 3.5. And it's also interesting to see some other, so the blue, all the languages in blue here are open source languages, and for the most part, languages in black are not. So that's one thing I wanted to. So really, the last 2 decades have really seen the rise of open source languages sort of taking over the mind share in this space. So R was also, from the beginning, designed to be an interface language. So this schematic is showing, it's actually John Chambers' notes, who was one of the creators of the S language from 1976. And this is really showing their initial concept of what they wanted this new language to be. It was really meant to be a wrapper around Fortran modules. And the other main thing they wanted to stress was that it was supposed to be used interactively. It was an interactive first language. So a lot of the design decisions were made to make interactive use easier. And also, down at the bottom, you can see that they were already using sort of a functional style interface where you have a number of named arguments, and that function call would return a value. So what makes R different than some other programming languages? So this quote is sort of interesting. So basically all programming languages have a hello world example. I feel like the hello world for R should, rather than being just printing the string, it should really be fitting a linear model. For a statistical programming language, that's one of the things you really have to be able to do. And being able to do that model fit concisely and correctly is really important. So I think that's something to keep in mind. The other thing is John Chambers says this quote about S, that everything that exists in S is an object and everything that happens is a function call. So you can really, for the most part, there's the concept of a statement in the S language. Everything is really a call. So now I just want to sort of demo the interface, or show you some sort of how R looks. The other thing that I think differentiates R from a lot of other languages is everything is a vector. So even things like numeric literals. I'll restart my R session. It seems to not be. Okay. So I'm just using the RStudio notebook right now, but the output will be down below here. So basically everything is a vector, which means that you can index into them. So even things like numeric literals are actually a vector. You can get the first element of a number 1. You can even get the first element of like a true value, which is kind of weird as well. But I think that's important. It actually shows that all the primitive types in R are vectors, even the one element types. So you can create a vector using this syntax. And then the other important thing to note is that most functions in base R are vectorized. So if given a vector of greater than length 1, it will loop implicitly within the function and produce an output of the same size as the inputs. So, and that includes things like plus and division. So you can run all of that in one statement and get a vectorized result. And this is true for things like numeric operators like plus and minus, but also for other functions that you might not necessarily think are vectorized. So if we the letters object just holds the letters in the alphabet. So if I take the first 4 of those, I can run and then there's this toUpper function that can take just a single value, and paste, which can also take a single value, but also both of those functions are also vectorized. So if given a vector, they will they operate on both of those, on all of the individual elements in the vector. So in a bunch of my examples, I'm going to be talking about this mtcars data set, and if you're not familiar with that, it's basically a data set of car data from 1974. This is from the Motor Trend magazine, and it has a bunch of different models of cars, the miles per gallon, fuel economy, as well as characteristics of the various cars like weight and horsepower and quarter-second time. So we can look at what that data looks like with this is a data frame, which is essentially just parallel vectors, all the same, that all have the same length. You can see what this data set looks like. Basically, we have all of the model names as the row names, and then our features are the columns. And then I said that the hello world for R is fitting linear model. How would you actually do that? We would use the lm function. And we give it 2 arguments, the second of which is the data set we just looked at. So that's our data frame. The first argument is this formula, this data formula, which defines how we want, what we want to build our model, what features we want to use to build our model. So here we're trying to predict the miles per gallon based on the horsepower and weight. And the other thing to note about this formula method, or this formula argument, is that these variables are not, do not exist in my global environment. These variables are being looked up in the mtcars data set. So this argument is actually not being evaluated and directly. The expression is being captured, and then those values are being looked up in this data, in the past data within the lm function. So if I now run this function, we get an object that contains the result of the fit, and then we get the coefficients, the intercept, and the coefficients for the 2 variables, and we can run summary on the object to get more detailed summary information. And then R also provides a plot method for these objects that give you some diagnostic plots to be able to plot this to make it more bigger. They give you some idea of how well your model is fitting the data. And there's also the generic, a regular plot. You can also plot each of the variables individually with just the plot function. And the main thing to note here is, again, this plot function is using so-called non-standard evaluation. So these labels are actually the expression that I pass to the call to the plot function. And so they're actually being captured during the invocation of the plot function and then used within to display the plot. And this, so typically in programming languages that would not have this functionality, you would have to supply those labels as additional arguments. In R, we don't have to do that. You can also, there's a function width that will allow you to evaluate all of the expressions inside of that call in the context of a data set. So here we can use width with our mtcars data set and again plot it. And you see that the miles per gallon and horsepower is again looked up to what we passed the call. So last thing I'm going to talk about in sort of this introduction to R. So you may have heard of the ggplot package. It's basically how that would work. So ggplot also does this non-standard evaluation. We pass it the empty cars data set, and then there's this AES function that allows you to bind aesthetics from your data set to the plot. So here we're binding the horsepower to the x axis, quarter-second time to the y-axis, color, miles per gallon to the color of our plot, and the model of our cars as a label. Then we can create points. We want points in our plot, and we also want a text object that corresponds to the model. And finally, one really nice feature of ggplot2 is you can easily facet a large number of plots based on certain things. So in this case, we're faceting by the number of cylinders in each car and then number of gears. So if I run that, then we get this array of plots that corresponds to that data, where we have the gears on the columns and the cylinders on the rows, and then each of our points that corresponds to one model. You can see things like the Porsche is a very fast 4-cylinder car, and interesting, the Ford Pantera is like one of the fastest 8-cylinder 5-speed cars in this data set. Great. Okay, so that's sort of R as a language. This talks really about extending R. So this plot is showing the number of packages available on CRAN, which is the package repository for R, from 2000 to the present day. Essentially, so back in 2000, there was really only a handful of packages available, only about 20 or 30. Today, there's over 1,300 packages. And these packages are doing a wide variety of different things. So there's the things you might expect in a statistical programming languages, like packages for manipulation, like data table and dplyr, packages for plotting, ggplot2 and plotly, packages for doing modeling, various types of modeling, like random forest models, the survey package for doing survey data, Caret, which sort of lets you do a bunch of different modeling with the same interface. But our packages also do some things you might not expect, like reporting. So there's a bunch of packages around generating reproducible reports. There's even so the book down package lets you write books in Markdown that output to both HTML and PDF. And package down will create a nice HTML website for your R package. You can also do things like web scraping in R, and people do this all the time with HTTR and RVest packages. And there's even more complex web app frameworks such as Shiny and OpenCPU that allow you to have interactive, reactive visualizations and reporting on your data. So I should also mention that sort of this large amount of development in the package space is really contrasted by a relatively conservative development in the language itself. So I mentioned that most of R really strives for compatibility with S and S back in sort of 1993. So like has really like driven, the language itself has not changed a great deal from that time. So really most of the current day development is really in the package space. So now I'm going to go through a few different examples of ways that we have sort of been trying to push the boundaries of our syntax and sort of extending the language with different packages. So the first one is really doing some sort of nicer ways of doing string interpolation with the glue package. So in base R, if you have like 3 variables and you want to interpolate them into a string, you do it with the paste function. And this works fairly well, and it's fairly performant as well. But it's sort of cumbersome to use, and it makes maintenance somewhat difficult because you have to quote each of the literal parts of the strings, and then insert your variables where you need them, and then put in, if you have another part of the string, you need to quote that, and it gets very cumbersome over time. So the glue package allows you to instead have a template that's a single string literal, and then inside the template is our braces that have the code you want to evaluate. And so all the code inside the braces is actually parsed and then evaluated by the normal R parser. Or, yeah, normal R parser. And this really allows you to embed these values directly in your strings, which makes it much easier to see, based on the template, sort of what your output would probably look like. And then also, it's easier to maintain because you can see exactly what values are supposed to be inserted where. And because this is geared towards the R ecosystem, it's also vectorized. So if we have our empty cars data set, we take just the first few rows of that, and then pass it to glue data. We get a vectorized result. So we have our model and our horsepower, and we get a vectorized result. So each line corresponds to the same line, a line of the data set. So the next example is piping and chaining with the magrittr package. So the example I'm going to go through is really using Little Bunny Foo-Foo. So you're probably aware of this nursery rhyme, Little Bunny Foo-Foo, hopping through the forest, sweeping up the field mice and bopping on the head. So if we convert that to code, this might be what it looks like. So we have Little Bunny Foo-Foo, and then hopping through the forest, scooping up the field mice and bopping them on the head. And you might notice from this code that there's a bunch of duplication. You have to, for each line, each call, you have to pass the old object and then assign it back to the object. And then for each additional call that you add to this file, you have to keep doing this duplication. And it's very easy, especially if you decide to rename one of these objects, to forget to do it in one of the steps or things like that. So it's very easy to make mistakes in that case. So another alternative way to write this would be to do nested calls. And the problem here is really sort of the so-called Dagwood sandwich problem. So it's essentially you have this huge sandwich of various parts, and it's hard to match up. The arguments for scoop end up down here, and the arguments for bop end up way down here. It's actually really hard to, and you also have to read this inside out, right? So you first have your foo-foo, and then it's hopping through the forest, and then it has to scoop up the field mice, and then bopping them on the head. So it's much harder to read code that looks like this. So the magrittr package allows you to use a pipe interface, which is similar to pipes you would have in a POSIX shell or in F#. And the pipe operator is over here, and the syntax is really the parentheses denote user-defined binary operators in R. So that's really defined by the language, and then within the parentheses, we use an arrow to indicate sort of the direction that the flow is going. And this is also similar to the F# operator, pipe operator. So this is much easier to read. You basically have your little bunny who's hopping through the forest, scooping up the field mice, then bopping them on the head. And a good way to, when you're reading code like this, is to use the word then for the pipe operator. So how this is actually implemented, well, this isn't exactly how it's implemented, but a good framework for how this works under the hood is the pipe operator during runtime modifies the AST of the right-hand side to insert a period as the first argument in the call, and then assign the result of that call to a period, and then it does this each time that operator is called. It does this, so you go all the way down the pipe, and you end up with code that looks something like this, where each call is assigned to the period and goes along. And this also allows you to use, if the argument that you want to pass along to the next stage in the pipeline is not the first argument in the function, you can use the period to denote where that argument should be inserted, or that result should be inserted.
Is period a variable name?
Yeah, it is. Yeah. So period, just a period is just a variable name, and it's a valid variable name. So yeah, I don't advise you to typically name your variables period, but it is a valid name.
But comma isn't.
But comma is not. That is true. Yes. Yeah. So this is sort of how it would look in practice. And this is basically just doing a simple subset using some of the functions we've used before. Simple subset of our data set for cars only over 100 horsepower, and then doing a linear model. And here I'm using the data. I'm using this period to denote where I want to pass the result of the subset in this lm call. Because if you remember, lm takes the data as the second argument rather than the first. And then I can call summary on this to get the summary of the model fit. So another example of where we are using, we're doing some extensions of R is in the dplyr and rlang packages with tidy evaluation. So first I wanted to talk about dplyr in general. So dplyr is a package for data manipulation. And if we load the package, and then, so this code is showing, I'll make it a little bit bigger. Basically, we're taking our mtcars data set, grouping by the number of cylinders, so that sort of partitions our data by that variable. And then summarizing, so for each of those groups, we want the mean number of horsepower, so the mean of the horsepower variable, and then the number of cars in this case, the number of observations in that group. Then we also want to arrange in descending order those results by horsepower, and filtering only for groups that have more than 5 members. So you can see sort of how the pipe that we talked about earlier fits well with this framework, because we have a bunch of calls that build on top of each other. And if we run this, then we get our results. So we had 3 different groups, and these are the mean horsepower and number of observations. So the sort of one neat thing about dplyr is it's able to work with different backends. So by default, it's just using a data frame backend. So this is just in-memory data. But you can also use backends that would be a database. So if and this example is using SQLite, but this will work with a wide variety of SQL databases, like Postgres, or even things like Google BigQuery have backends for this. So if I just create a simple connection to this database, and then copy my mtcars data set there, and then create an object that represents that mtcars table, I can then use this object and change nothing about my, actually I'm going to take out this last part, change nothing about my pipeline and run that code. And this is now running the code not on my, well, it's all running on my computer because the database lives on my computer, but this actually, all of the calculations are now happening in the database rather than in R. And you can actually see this, and this is happening because dplyr is dplyr is actually generating SQL instead of running our code in this case. So based on that input object, we can generate SQL. And just by, without changing any of the R code that would do these manipulations. And the SQL, depending on the variety of database you're using, we have different translations. So if you're using Postgres, it will do the right SQL translation for Postgres, etc.
How do you set that?
So it's based on the connection that you input. So in this case, I had a SQLite connection, but if I was connecting with a Postgres connection instead, and created an object based on that connection, then and ran the same code on that, it would generate the appropriate code. So it's just doing like method dispatch based on the object, the input object. Okay, so if we have, so let's say we're doing a few different similar analysis of this data set. We're grouping by a certain variable and then summarizing we want the mean of a different variable. So first we do it with cylinder, then we want to do the same thing, but instead of group by cylinder, we want to group by gear and get the mean of the weight, or group by the number of carburetors and get the mean of the quarter-second time. So all of these things are basically doing the same two operations, just with different variables. The natural thing to do in that case is to put this pipeline inside a function and pass the variables we want to group by and summarize by as arguments to the function. So if you try to do that, and then run this, we'll get an error. And essentially, the reason we're getting this error is because this dplyr is doing non-standard evaluations. So rather than getting the value of the grouping variable, which is what we wanted, we're getting the expression group var. You can tell this if we look at the abstract syntax tree of this pipeline. We see we're passing group var and summary var to the call, the mean, and the group by. And so in this representation, each of the, I don't know what color that is, orange boxes is a call, and then each of the purple are arguments to the call. And in this case, this is a named argument, which is why this looks different. So what we really want to do is quote those variables, so that captures the expression of the variable rather than the value. So if we quote these variables, we quote cylinder and miles per gallon, which is what we wanted to call this function with, and then unquote them with this bang bang operator, which is just two unary negation operators together, which we make those things mean a different, have different syntax or different semantics than they would typically in R. For this case, if we do that and then use our AST column, we can see that they were substituted appropriately how we wanted. So instead of calling group by with the grouping variable, we're now calling it with cylinder and miles per gallon. So to change our function to take advantage of this, we use the enquote function, which quotes the variable and returns the captured expression, and then unquote those captured expressions with the bang bang operator. Okay, so if we now define this function and then call a group mean with the cylinder and miles per gallon, we get the result that we wanted. And then we can do our other combinations as well and see they all work. So now our function, this group mean function, is now doing non-standard evaluation, capturing the argument, the expressions of these arguments, and then using them inside our call to the dplyr functions. Okay. So just to go over that again, so lots of functions in R are so-called quoting functions, so they take arguments as the expression rather than the value of the argument, such as things we've looked at before, subset, width, and plot. So in doing tidy evaluation, we use inside R. So if we want to make one of our functions a quoting function, we use this enquote function call with the variable name, and then typically we just assign the value back to our variable. And then the flip side of that is unquoting functions. So we have this bang operator that you can use to unquote the value, which actually substitutes the expression inside the call, and then that's evaluated by in this case, dplyr. So this allows you to use the same dplyr pipelines and non-standard evaluation within functions that you would use outside of functions. It's also robust. So really base R doesn't have an exact equivalent to this because there's no equivalent of this bang operator in base R. There's no way to unquote your the captured arguments. So do people actually use these syntax extensions? So these plots are showing on the x-axis time since 2014 to today, and on the y-axis is weekly downloads of each of these packages from the RStudio CRAN mirror. And you can see, so this is dplyr, magrittr, the rlang, which implements the tidy evaluation, and glue. And all of these packages have over 100,000 weekly, over 100,000 weekly downloads today. So they're all quite widely used in the R community. Okay, so this is all stuff that is sort of in CRAN packages already. So this last part I'll be talking about is the altparsers package, which allows you to use alternative parsers inside a package. So this is available on GitHub at my GitHub and altparsers. This package has multiple sort of example parsers within it, but they're really just proof of concepts. It's also user or package author extendable, so if you had a different parser you wanted to use, it's very easy to use it in the same framework. Really, the altparsers package provides sort of structure around the parser, and it just calls the parse functions that you supply it. And also, you can mix multiple parsers in the same package. So if you, for some reason, want to use the regular part, well, this might make sense to use the base R parser for part of your code, for the majority of your code, and maybe use an alternative parser for a subset of your code. But you can even use two completely new parsers. And I should mention that all of these parsers eventually have to generate like valid R, AST. You can't just generate like anything. It eventually has to be, it's still being evaluated by the normal R evaluation runtime. And the altparsers package also provides REPLs. So if you give it a parser, you can generate a REPL. So that allows you to use these alternative parsers interactively. And all these features allow you to sort of experiment with these alternative parsers in package space. So you never have to actually modify base R code at all. You don't have to change the R runtime at all to use these. The first example is the S expression parser. So this is really just a very simple proof of concept. It's definitely not fully featured. And essentially, I wrote it to illustrate a completely de novo parser. So this doesn't use the native R parser at all. The next example is sort of a Python style parsers. So this mainly does function, allows you to use syntax very similar to, it uses base R syntax for everything but defining code blocks. In that case, it uses, instead of braces, which would be typical R syntax, it allows you to use semantic white space like Python. So this would be how you would define a function in this case. The last example is the tidy parser. So this is sort of built on top of the base R parser. It embeds a modified version of the base R parser in the package. And some features of the tidy parser are raw strings. So typical quoted strings in R have backslash escapes. The raw strings essentially treat the whole string as just raw text, so you don't have any backslash. The escapes of the backslashes don't mean anything. This is useful for writing regular expressions, and also things like pass on Windows. Second feature is glue strings. So this converts this G and then a string to the equivalent call to the glue package. Again, this is sort of just a nice to have feature. Native pipes. So the way that these native pipes work is at parse time, the AST that's generated is converted from this pipe syntax to the equivalent nested calls. And this is useful because the magrittr pipe does its manipulation at runtime, which has some performance overhead. And it also makes debugging more difficult because the traceback contains sort of the internals of the magrittr manipulation. And the native pipes do all of their, it just generates the AST at parse time, so it doesn't have any performance overhead during runtime, and it also doesn't have any of these additional calls in the tracebacks, which makes debugging much easier. And then finally, it has a simple, more concise way to generate lists. So this would generate a 4-element list with a 3-element list inside as the last element. So how would you use these interactively? So you can start a REPL with the REPL function, and then you just pass that function the parser you want to use. And then, so this will generate, this is how you do start up a new REPL with that parser, and then you can quit any of the REPLs with calling Q. I mentioned you can use this in packages. So if you have scripts that use one of these alternative parsers, you put the code for those scripts in your inst directory, in directories within your inst directories to make sure that they're installed with the package. And then you export or document the functions as you normally would with an R package. And then the only other thing you have to do is in the onload function for your package, which is run automatically when the package is loaded, you have a call to the src function in the altparsers package with the folder that your scripts live in, the package that you're sourcing them into. In this case, the EX package is just an example package, and the parser you want to use. So I have scripts in the sexpression folder. I want to use the sexpression parser. That's how I do it. And then if I want to use the tidy parser, you can do it like that. And finally, just to show that this actually is not just hand wavy, it does actually work. This. All right, first you have to start R. Okay, load the altparsers package. Then I can start up a normal R REPL. So this looks exactly like the normal REPL would. And I can just do normal R things, and this is just showing that the continuation syntax works as it would normally. And I can quit out the parser, But then I can also start up a parser with the s-expression REPL and use s-expressions in that case. So we can see our s-expression was parsed and evaluated as we'd expect. And quit out of that. And here I'm actually parsing up the Python version, Python style script. So this had the same code as my previous slide, but it was actually, if we look at the parsed expression, you'll see there's braces back in here. And basically how that parser works is based on the white space, it adds braces back in and then uses the standard R parser. So that's why there's braces in the parsed expression. Then we can evaluate that and just verify that this recursive factorial function actually works. But we can also start a REPL with this Python parser. And if we just use this logit function and call that works as well. And finally, we can do this tidy parser. So we can create a list. We can just look at our list and see that it created it successfully. We have a 4-element list, which contains a 3-element list. And then we can also use our native pipes to extract the 3rd element. So we get our 3rd element. And then also verify that the native pipes worked how we were expecting, and then run that again. And so this is actually converted to the equivalent nested call. So rather than, we don't see any pipe operators here, it's just the equivalent nested call. And then finally, we can use our glue strings and the raw strings in addition with our native pipe. And that gives the result you would expect. And again, if we look at the quoted value, it's not the easiest thing to see, but yeah, so you can see that this was at parse time, these were translated, the raw expressions were escaped, the glue call was added, and the pipelines were all converted to their nested equivalents. So we can put out that. So future directions on sort of where this altparser stuff is going. I think it would be useful to have like a survey of sort of the R community to see where they find the current R syntax painful, and maybe design a new parser based on this idea. Like I said, sort of R syntax we have today is really derives all the way back to at least 1993, if not earlier. So it would be nice to be able to update that if possible. And I think a survey would be a good way to do it. Right now, all these alternative parsers are really just sort of a research idea. We're not using them in any of our user-facing packages. So it would be nice to use some of these in a user-facing package and see how people like it. And then I was talking with a viral about his type annotation. So he has this project for adding type annotations to R, and it uses a modified parser. So typically previously he was modifying the base R source code to add this parser, and there's a bunch of hoops you would have to go through to get those changes added to base R. You have to convince the R core team to accept the changes, and they're fairly reluctant to do large changes to that code at this point. So this package, this alternative parsers package, would allow him and other people to experiment with these types of parsers without having to change base R at all. So he can use his type annotations and add his type annotations to R, and we can use it in our packages on CRAN without having to change the base R runtime at all. So The 4 packages on CRAN are all available. You can use them today. And if you wanted to try this altparsers package, it's available on GitHub. And that's me, and I'm happy to answer any questions. All right, well, thanks everyone for coming.
Thank you.